A line spectrum, on the other hand, is produced by individual atoms giving off electromagnetic radiation at precise frequencies. This can be regarded as the signature of the element. The absorption lines occur at precisely the same wavelengths as the emission lines. Our understanding of the hydrogen atom took a giant leap forward in 1913. In that year, Niels Bohr, who lived from 1885 to 1962, introduced a model that allowed him to understand the line spectrum of hydrogen. Bohr combined the elements of classical physics with the ideas of quantum mechanics. Thus his model is a hybrid that spanned the gap between the physics of Newton and the newly emerging quantum physics. Bohr's model of the hydrogen atom is based on 4 assumptions. The first 2 are specific to his model. They are as follows. The electron in a hydrogen atom moves in a circular orbit about the nucleus. Only certain circular orbits are allowed. In these orbits, the angular momentum of the electron is quantized, just like energy is quantized in Einstein's photon model of light. The next 2 assumptions are more general. Electrons do not give off electromagnetic radiation when they are in an allowed orbit. Thus, the orbits are stable. Electromagnetic radiation is given off or absorbed only when an electron changes from one allowed orbit to another. If the energy difference between the 2 allowed orbits is delta E, then the frequency, f, of the photon that is emitted or absorbed is given by delta E is equal to hf. We now proceed to the derivation of Bohr formula for the stable orbit of the hydrogen atom. We know that the electron and the proton in the nucleus exerts an attractive force towards one another. We also know that they have masses and the electron is in seemingly circular motion around the nucleus. Hence it has a centripetal acceleration which consequently gives rise to a centripetal force. Therefore, it must follow that the attractive electric force is equal to the centripetal force. We can write this relationship using the equation F sub E is equal to F sub C, where F sub E is the electric force and F sub C is the centripetal force. We can work on these equations to find the stable orbit and the average velocity of the electron in this orbit. Since F sub E is equal to electric constant K times Q sub 1 times Q sub 2 all over R squared, and F sub C is equal to mass m times velocity v squared all over r. We have K times Q sub 1 times Q sub 2 all over r squared is equal to m times v squared all over r. And we know the value of the charges, which are both equal to 1.6 times 10 raised to negative 19 C. Then we have Q sub 1 times Q sub 2 is equal to E squared. A negative sign is affixed, so we know that the electric force in effect in the given situation is conservative and attractive at the same time. We can simplify the formula stated above as K times E squared all over R squared is equal to mv squared all over r. Solving for the velocity of the electron, we have taking the square root of both sides gives us the velocity of the electron in the hydrogen atom. V is equal to square root of K times squared all over mr. We can also determine the radius of the electron from the nucleus of the atom. We solve for the allowed radius of the electron in the hydrogen atom and find out that r is equal to Ke squared all over mv squared. The velocity and radius are related to one another, which in turn related to the kinetic energy of the electron in this orbit. We know that the formula for the kinetic energy is given by Ke is equal to 1/2 mv squared. Substituting the formula of velocity for v in this equation gives us Ke is equal to 1/2 m times K times E squared all over mr. Ke is equal to 1/2 Ke squared all over r. K is equal to 1/4 pi epsilon naught. We have E is equal to negative E squared all over 8 pi r epsilon naught, where epsilon naught is called the permittivity of free space. Each allowed orbit will and can only contain a discrete amount of energy. Hence it is otherwise called as energy levels.